Hello again, students, and welcome to a new nugget on biomass for energy. You see, I have a cat here, so there might be some noises, or you might think I'm behaving strange, and then that is because of the cat. The cat will not lecture. This lesson deals with the system solutions, and today we shall have a look at how forest biomass is used in modern Swedish applications. As you might know, is solid biomass, and that is mainly wood fuels, the dominant single energy source in the Swedish energy system. About 35% of the total energy input in the Swedish system is biomass. It's followed by oil, some 30%, and then hydroelectricity and nuclear electricity equals about 15% each. So they are on the shared third place. And then there are other sources like wind, waste, heat pumps from hydro, heat pumps from geothermal sources, and so on. So considering that 35% of the total energy input into Sweden is biomass, it is natural to select at least one example of modern biomass use from Sweden. The first thing we have to consider is what is really wood fuel. Now, woody biomass, wood fuel, includes several assortments. First, we have the fractions that consist of parts of the tree. Here we'll find branches, thin stems, and the like. Then there are the fractions that consist of industrial byproducts. These fractions will have quite different properties. You will find the assortments described briefly in the Busy-Plan Handbook, Chapter 3.1. The example we shall look at is one where forest fuel, felling residues, is dominant. Looking then at the Swedish wood fuel supply, out of a total annual forest growth, about 105 million cubic meters, or about 20 million not accessible. This is partly because of terrain, partly because they are inside national parks or other protected areas, but also because of other reasons. So the annual felling is about approximately 85 million cubic meters, and out of this is 5 to 10 million left in the forest. Again, may the reasons be different. There will be two main types of fuel coming out of the forest operations. Forest owners and people living in the countryside do quite often have wood-fired boilers in their houses. So all over the country is about 4 million cubic meters used as firewood. But then there is the thin material, branches, tops and thin stems. This amounts to about 12 million cubic meters, and this is the flow that we are about to look at now. The first step to guarantee a good fuel quality is taken already during harvesting. The harvester operator must be well instructed to put the fuel fraction to the side. If the harvester runs over the fuel assortment, will the ash content increase and the quality will be significantly lowered. Quite a lot of material will also be lost in this case because it will be pushed down into the ground and cannot be recovered. Now look at the first video, Harvester, and you will see how this part of the operation looks. During the first month is the fuel fraction allowed to stay on the ground so that parts of the green material can dry and fall off. Since that material is the most nutrient rich, you want it to be retained across the felling place. Approximately 1 or maybe 2 months after harvesting is the material piled in windrows accessible from the forest roads. The windrow is a porous structure and is covered with waxed paper as a primitive rain protection. Since the windrow is porous, does the material dry while at the same time microbiological deterioration is minimized. Approximately a year after harvesting is the material chipped into containers and transported to the energy plant. Once the material is chipped and the cell cytoplasm is exposed, does the biological deterioration gain speed. So, as we said, approximately a year after harvesting is the material chipped into containers and transported to the energy plant. As you learned in lesson 2, will the microbiological activity in the chip pile also imply heating of the material? This is a natural thing and cannot be stopped. So it is very important that the fuel storage by the energy plant takes the risk for fire into account. Almost 200 fire incidents in forest fuel storages are reported annually in Sweden. These incidents include not only piles at energy plants but also at sawmills and other wood-based industry. Not all develop to fires, but the number gives you an idea that the chip piles must be monitored for the risk of fire. A burning chip pile cannot be extinguished. The only thing you can do is to isolate it and prevent fire spread and wait for it to burn up. So plan your handling to avoid too long storage times and too high piles and other mistakes. Let's now look at an example. As you know, will any fuel-based electricity production cycle generate waste heat? There are 2 ways to view this unavoidable heat. Either you build cooling towers or use seawater or rivers to absorb the heat. In that case, you will maximize the electricity production efficiency, as you have already learned in a previous nugget in lesson 3. Or you turn the heat loss into a valuable product and sell it. In that case, you sacrifice a bit of the electricity, but in some climates the heat demand is big enough to make this a feasible option. This is called district heating, and the process is CHP, combined heat and power production. But in summer, you will not be able to sell very much heat. And if you limit your heat production, you will also automatically limit your electricity production. So to maintain a high electricity production also during the hot season, you want to make good use of the heat and get paid for it. And you can do that by using the heat to produce and sell district cooling. The basic idea with this type of plants is to maintain a high electricity production all year round. So let us have a look at how this is accomplished. So now we are talking CHPC production, and the second C in CHPC stands for cooling. The idea is to produce and deliver cold water to the customers, just as the idea with district heating is to produce and deliver hot water. Just like with the district heating water, you want to deoxygenize the water and circulate it in a closed system. You will find an introduction to this in chapter 408 or 408 in the Busy Plan Handbook. In the case of district heating, you pump out water at, say, 95 degrees C, and you get it back at, say, 45 degrees, and then you heat it up and pump it out again. With district cooling, you deliver water at, say, plus 5 degrees, and then you get it back at, say, plus 20, and then you cool it down and pump it out again. For cooling, you use hot water and a heat pump. In a heat pump, you absorb heat by vaporization at a low temperature, and then you release the heat again by condensation at an elevated temperature. Now let's look at what the customers want. We assume, just like before, that the plant is supplying a city. So the customers are households, offices, and public sector facilities. In winter, these customers want to have heat, so then district heating is the main product. But there is only a limited need for cooling. In summer, there is a limited demand for district heating, but then there is a bigger need of cooling. Both seasons do the customers want to have electricity, and the electricity production inevitably generates heat losses. And these heat losses are what we sell as district heating. So what we want to do is to use the district heating produced from the outlet steam to produce district cooling. To do that, the smartest way is to use an absorption heat pump. And let's now look at the theory and how this works. It is well known that the vapor pressure of the solvent is reduced when the concentration of the solute in a binary mixture increases. This means that if we assume two vessels containing a dilute and a concentrated solution, and we assume they are reasonably at the same temperature, then there will be a cross-flow of vapor. So the solute will vaporize to the left and will then condensate to the right. Vaporization requires energy, while condensation releases energy. So there will be an energy transport from left to right, and the vessel to the left will cool down. With a closed system like this will, ultimately, an equilibrium be established. So we have to avoid that equilibrium. To stay away from the equilibrium, must the solution in the absorber, in the energy absorber, be maintained at a low concentration. So this solution is pumped to a distiller where heat is added to vaporize the solvent. Using the example from the previous slide, this is to say that the ammonia is boiled off. The dilute absorption liquid, almost pure water, following the same example, is cooled and returned to the absorber. The solvent vapor, ammonia, is cooled until liquid and returned to the evaporator. With this system, can the evaporator be maintained at a low temperature with a system where the main energy use is heat and not electricity. Vented away from the cooler is all the energy equivalent to the electricity input to the pump, all the heat energy input to distill the absorption liquid, and all the evaporation energy absorbed in the evaporator. The cooling capacity of the heat pump is only the energy absorbed in the evaporator. So the coefficient of performance, the COP for cooling, will always be less than unity. Most common in absorption heat pumps for this application is to use lithium bromide in combination with water. Using that, can the evaporator be maintained at some 4 to 5 degrees Celsius, while the need of heat in the distiller is a reasonable district heating temperature, around 90-95 degrees. Let's now look at a practical case. And the case is a 104 megawatt thermal circulating fluidized bed unit, Sandvik 2, at Växjö Energy in Sweden. The boiler house and the flue gas losses amount to approximately 8 megawatt, so the maximum steam production is about 96 megawatt. The turbines, a high pressure turbine and a low pressure turbine, and the generator only have 38 megawatt generating capacity, which was enough when the plant was commissioned. The losses in the district heat exchangers are negligible, so the district heating will then amount to about 58 megawatt. The absorption heat pumps can take 10 megawatt surplus waste heat from the district cooling customers, and the COP is 0.7. So that means it needs approximately 14.5 megawatt district heating for its operation. And then it also takes about 1 megawatt electricity for the circulation pump. This all, total 25.5 megawatt, are unavoidable losses from the system. So then the total commercial products are 37 megawatt electricity plus 43.5 megawatts district heating plus 10 megawatts district cooling. So this is a total of 90.5 megawatt commercial products delivered with an input of 104 megawatt fuel. The total system efficiency thus becomes 87% based on fuel input. Looking now at the heat balance for a system like this, it is important to understand that from a strict energy flow point of view is the commercial product called district cooling, not a plant output. To provide district cooling is to invite and allow the customers to dump their waste heat into the energy plant. So the district cooling is actually an energy input to the plant. The waste heat is brought into the absorption heat pump and is vented away together with the heat energy needed to take out the waste heat from the water where it was stored when it came from the customer. From the heat pump is also vented away the electricity needed to circulate the absorption liquid inside the heat pump. So in the overall heat balance, does the cooling show up as an input and as a loss? District cooling is not a delivery of energy. It's a waste handling service. It is an offer to the customer to dump their residual heat into water and then to get new cold water in return. So while the previous case was at high load, let's now look at a low load case. Let's look at the balance on a hot day when the district heating is used only for hot tap water, which is less than 10 megawatt. The turbine can only be down regulated to approximately 15 megawatt. So the turbine efficiency is now slightly lower, and so is the total efficiency. Looking at this slide, You will understand how the calculation is done, and this is the type of calculations that you will do in the homework.